Okay, so welcome to another session of our reading group on the assumptions of physics. And today we're going to look at differential topology. And so let's share as usual. And I'll share in the chat the link. There we go. So should we just get started, Artem?
Okay, so reversing differential topology. In the previous sections, we saw that elements of differential topology and differential geometry started appearing. We employed a generalization of the curl, and we used the form omega AB to lower indices, much like one does in general relativity with the metric tensor. Since we will use these tools more and more, we should take a detour and understand the physical significance of the tools themselves. We will end up with a generalized notion of integral and of differential operations that will work with an arbitrary number of dimensions. We will also conclude that to reach the full potential of reverse physics, we need to apply the same techniques not just to the equations themselves, but to the mathematical tools we use to formulate them.
The main reason we are forced to abandon vector calculus in favor of differential topology and geometry is that vector calculus works in 3 dimensions, but does not generalize to an arbitrary dimensional space. Special and general relativity, for example, live on a 4-dimensional spacetime. Hamiltonian and Lagrangian mechanics live in phase space, which can have an arbitrarily large number of degrees of freedom. Similarly to what we have done with the equations, we will start from the expressions of vector calculus, see their limitations, and construct generalized ones. We warn the reader who is already familiar with differential topology that this process will give us notation and concepts that are slightly different from what is used by mathematicians. We will discuss these differences at the end of the section.
Who's next? Rudra? Oh, Rudra, you're muted. That's the problem.
I see the settings got changed. Sorry about that. The first tool we need to generalize is that of line, surface, and volume integrals. For example, the mass m within a region V can be understood as the sum of the contributions of a mass density rho within each infinitesimal volume dV. So we have m of V equals the volume integral of rho dV. Similarly, the magnetic flux phi through a surface sigma can be understood as the sum of the contributions of the magnetic field B over each infinitesimal d sigma. So we have flux on sigma equals the surface integral sigma of B dot d sigma. Lastly, the work W over path gamma can be understood as the sum of the contributions of a force field F over each infinitesimal segment d gamma. So work on the path gamma is line integral over gamma f dot d gamma.
Note the pattern. The functionals w, phi, and m all take a region of space, while f, b, and rho act on infinitesimal regions. However, the pattern is not completely consistent. In the line integral case, we have the product between a vector representing the force and a vector representing the displacement along the line. In the surface integral case, we have the product between a pseudovector representing the magnetic force and a pseudovector representing the normal to the surface element. In the volume integral case, we have the product between a pseudoscalar representing the density and a pseudoscalar representing the volume of the infinitesimal region. Each operation is slightly ad hoc. Moreover, a surface has a single perpendicular direction only in 3 dimensions. In 4 dimensions, for example, there are multiple different perpendiculars to the same plane. Lastly, they all require a notion of product between vectors, an inner product, which in differential geometry is only defined on Riemannian spaces, those that define a metric tensor. That is, those spaces in which angles and distances are well defined. In physics, we are so used to working with spaces that have an inner product that it may seem that all spaces provide one, but that is not the case. In phase space, there is no way to compare differences in position with differences in momentum. Therefore, we do not have a metric to take a scalar product. There's no overall notion of distance and angle. In general, if we imagine the space that represents all possible outcomes of a blood test, this will form a manifold, as each test can be fully described by a finite set of continuous quantities. In this space, there is no natural notion of distance and angles between directions. There is no notion of geometry. As we will see, the notion of integral, the idea of a quantity that can be understood as a sum of infinitely many infinitesimally small contributions, does not require either a particular number of dimensions or a notion of distance and angle.
And please do interrupt if there is questions or if there is something not clear. Tobias?
I'm next, right?
Yep.
Okay. Suppose we understood F, B, and rho not as above, but as maps that for each infinitesimal region return an infinitesimal contribution dw, d phi, dn. We could simply write w of a path gamma is the integral over gamma of infinitesimal dw's, which is then f of dy. And then similarly, we basically don't have any kind of inner product anymore. We just have functions that take infinitesimal somethings. This pattern is straightforward and more easily generalized. We call these functions of infinitesimal regions K-forms, where K is the dimensionality of the infinitesimal region they take as an argument. The force in this notation is a one-form or covector, as it takes one-dimensional infinitesimal regions, i.e. vectors. The magnetic field is a two-form. The density is a three-form. We can also say that a scalar field, like the temperature, is a zero-form, as it takes points, zero-dimensional objects.
Since K-forms act over infinitesimal regions, they will have some key properties. First, note that each infinitesimal region can be understood as a parallelepiped, and a parallelepiped is fully identified by its sides. Therefore, a K-form can be understood as acting on a set of infinitesimal displacements, the sides of the parallelepiped, whose number matches the dimensionality of the form. One form will take one displacement, two displacements, and so on. Second, as they are linear functions on the infinitesimal regions, they will also be linear functions of the vectors that define these infinitesimal regions. Lastly, all forms must be antisymmetric because switching the order of the sides does not change the parallelepiped, but it changes its orientation.
We can write displacements and forms in terms of components and basis elements. And do you want to go through that, Gabriel?
Yeah, so basically this is the prototype for a displacement. dp is just the differential on the coordinate times the basis. And then for all the different forms, you have the the component in terms of the cobases, and the cobases will be a function that's going to be 1 when it follows a basis, right? So this only acts on 1 vectors, this acts on 2 vectors, and this acts on 3 vectors. It's basically how it works.
The anti-symmetry means that switching the indexes introduces a minus sign. For example, Bija equals minus Bji, and rho ijk equals minus rho jik. Therefore, our integrals can be written as this is just like substituting 1.73.
Yep. Yeah,
Okay.
you're just using this definition above here, right? And now you substitute it here, and then what you have is that whenever you have a dp, it gets contracted by this AI gets contracted by AI. So now the fi are acting on the dxi, and you have 1 displacement for each slot, right? For each dimensionality of the form.
And are we summing over double indices?
Yeah, this is all Einstein notation. So wherever
Yeah.
there is an index up and down, that gets summed up.
Each K form then is a fully anti-symmetric covariant tensor with 1 index for each dimension of the form. In this view, the Bx component of the magnetic field then becomes the B sub yz component. That is, instead of being the component that gives us the magnetic flux along the x direction, it is the component that gives us the flux through the yz plane. Similarly, rho xyz is better understood not as the value of the mass density at a point, but rather the value of the density over the xyz volume. The indices make unit dependency apparent as well. Byz must be in units of magnetic flux divided by units of y and z. Rho xyz must be in units of mass divided by units of x, y, and z in spherical coordinates. In spherical coordinates, b r theta must be in units of magnetic flux divided by units of r and theta. In fact, one can argue that these tools are here exactly to keep track of the units of the components.
We can go further and rewrite the integrals in terms of parameterizations of the surfaces and the components of the forms along said parameterization. We have equations 1.75.
So basically what we are saying here is that this is a line integral of a gamma. The gamma will have our parameterization in terms of a variable u. So you're going to go from AU to BU. And then what you're going to do, you want to express now this differential in terms of the u. So you have a chain rule here. But then when you're doing this, what you're actually doing is just a change of bases and getting the component of f over u. Right? So what you start here is with a form that have, essentially that gives you a value for each direction. And now you constrain direction along the curve. So you start with something that works in 3 dimensions, and you actually get something that it's only on 1 parameter, which is the parameter of the curve. And the same thing you can do for your magnetic flux and your mass. So you could imagine, for example, that if you have the force described in terms of self-parameterization and the curve in a different parameterization because it's more convenient, right? So maybe expressing the force is easier in 1 coordinate because you have some symmetry that the force, for example, is all vertical. But then the path, right, the path is curved, and so you use a different parameterization. This allows you essentially to merge the two, this expression, and then you basically rewrite the integral so that now it's easy to solve. Like this is also practical, but the point here that it should be clear is that you're going from the standard parameterization that you would have on the space itself to the parameterization of the curve, and then you can do it for both the line integral, the surface integral, and the volume integral. And so the point is that all these things can now be generalized to n dimension, to a K form in an n-dimensional space.
These expressions are useful to write the integrals in terms of an integral of K variables. This is particularly useful if the surfaces possess different symmetries than the forms, which allows one to use the parameterization appropriately.
Samir?
We now have expressions that are easier to generalize. If we denote Sk the space of all the k-dimensional subregions of an n-dimensional manifold, a k-functional Fk goes from Sk to R, is an additive functional that takes a k surface sigma k and returns a number. This can be expressed as equation 1.76.
Right. So we have the functional, this gets a surface, and then we express this as the integral of the surface over a form that takes an infinitesimal K surface element. And then this, since it's a form, can be expressed as a fully antisymmetric covariant tensor. These are all the different displacements. So these are now in X. And then you can say, okay, now I use the parameterization of sigma, and I express the parameterization of sigma with K U variables. And then I re-express the component in terms of those K variables.
Which is the integral of a k form omega k from Vk to R. Here, V is a space of vectors of infinitesimal displacements, and an infinitesimal k surface, d sigma k, is defined by an ordered set of k vectors. Therefore, is an element from the Cartesian product Vk equals V times V times V dot 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 times V. The K form takes an infinitesimal K surface d sigma K and returns a number. We now have a way to express local objects and integrals in a generalized way.
So I should note, I don't know if I note it later, like in principle, one could use multivectors instead of ordered set of vectors. The problem with that is that I always get this sort of 1 over k factorials around, and I don't quite know how to handle it in a sane way. And that's why I prefer to use this notation and do things like that. If anybody is ever going to help me understand how I can use multivectors without having the mass of that k factorial that I have to bring around, that would be nice.
Okay, can I just ask a question about this? If we
Yeah.
consider M, for example, M is a measure, right? So like a measure on like 3D space. So technically it's not any subregion, it's like any measurable subset that is like in the
This
SK.
the mass, you mean?
Yes, for example.
Mm-hmm.
Yeah, then like the sets I can like only measurable sets I can ask how much mass is in this measurable set, right?
Yeah.
So I guess something similar will hold for a line where I don't know exactly what that means.
Right. So we are assuming that there is the space of k-dimension. So for a line, you're going to have the space of one-dimensional manifolds that are also going to be differential in submanifolds. So you're going to have a differential embedded inside the space.
Okay, yeah, I was just wondering like what are the technical requirements to go from like a functional to like a form, basically, like an infinitesimal version. And for the mass, it is like it has to be sigma additive and absolutely continuous with respect to the back measure, for example. And we could show exactly then you find such a form, basically. And I wonder if I've never
Yeah,
seen.
you need the differentiability. So the only on the Lebesgue measure is not enough. Like you need you need to be able to write the density, right? So for example, it needs to be that it's absolutely continuous with respect to the Lebesgue measure, such that you can define a derivative, a radionickel derivative, and therefore have the
Yeah.
volume form.
I wonder if like, I mean, for now, we don't need to get into these details. I'm just thinking, like in general, if stuff like this, what the requirements would be for something that's not the mass,
Right.
which is
I
just
do
the panel.
not know actually, like if I have, so this has to be a linear functional, and we agree on that. I do
Yeah.
not know what are the conditions of the linear functional such that it can be written as a form. So here, basically, I'm cheating. I basically say that I have this is a K functional if it can be expressed as a form. So I basically define it to, yeah.
Great. I was just curious, maybe I will find it out myself. We can, I don't know.
Yeah, I haven't found a ready-made recipe, unfortunately.
Okay.
This is where like it would be nice to have everything that starts with sort of functional of subregions, and then you take the infinitesimal as a limit, so that you know when you can take the limit. Because there are other things that make more sense that we'll see later, like just to think of the integral form. But I don't have a way to do that properly.
I think for the one-dimensional case, the mass, the linear functional is also a one form for the one dimension, but in general, it's not true that every linear functional is also a form, because the form is consists of like the tensor, the antisymmetric tensor product,
Yeah.
just by construction.
But there has to be something like if you make a small variation of the what's it called of the surface, then the form will have to have a small variation in some kind of way. I expect that there should be a property that you can put on the functional that will allow you to characterize this. It's just I don't know.
Okay, maybe one last detour before I continue reading.
Yeah.
The space of subregions sounds a bit like Grassmannians, but I think Grassmannians are like vector subspaces, right?
Oh, I have to go and look at the definition.
Okay, maybe then.
So what's a Grassmannian in this case? Grassmannian. All dimensional linear subspace of the n dimension. So these are not necessarily
Yes.
subspaces, though.
Yeah, because like it can be curved basically.
It can be curved. It doesn't have to
Not
go through the
necessarily in the vector
origin,
space.
and yeah.
Yeah. Okay. Then let's continue. In the spirit of reverse physics, we ask, what are the physical assumptions that are required to use these mathematical objects? Note that we do not measure mass density rho directly. We measure mass m within a finite region V and the size of the finite region V, and we calculate the mass density by dividing the first by the second. The mass density rho is the limit for which the region V shrinks to a point. The same happens with other quantities. We do not measure force directly, but rather the work that a force performs, for example, by deforming a spring. In other words, we measure the finite value of the functional f over a finite region sigma, and the form omega returns the limit of f for infinitesimal regions. Note that it is crucial for f to be additive. That is, if sigma 1 and sigma 2 are two disjoint regions, then f of sigma 1, sigma 2 joined is the sum of the two. Physically, it means that the contribution of one subregion is independent from the other, because if this isn't the case, we cannot assign a unique value to each region. While this may seem a relatively harmless assumption, it may not hold in general. For example, suppose we have a system distributed in space. Given the mass-energy equivalence, the mass is an additive functional only if the interaction between the parts can be neglected. In fact, if the interaction energy at the boundary is so large that it is of the same scale of the mass within the regions, then it is not true that the total mass is simply the mass within each region. Therefore, if we write mass density rho, we have implicitly assumed that the interaction energy between parts can be neglected. While this is going to be true in a large number of cases, it is something we have to keep in mind. The functional f, in fact, is a more general physical object, as it may exist even though infinitesimal additivity fails. Can I assume like proton mass is something like that? If I look too far into the proton, like all of it is basically interaction energy.
Yeah, I don't know how to think about that. A question from the chat. Non-additivity is exactly the problem in general relativity. Mass of gravitational field is non-local. Yeah, it's exactly it. So yeah, I was thinking more of general relativity as Julius comments. So yeah.
Sorry, what did he say? Like the mass of the gravitational field?
The mass of the gravitational field is non-local, or the energy of the gravitational field is non-local. It's exactly that problem. Like it's you add energies at points. You're not just adding the energy at that point. You're also adding the gravitational energy, which it's interaction energy. So the point here is that not that I have a solution, is that you have to think about it because it's a tricky business.
If the functional f respects the limits in the sense that small variations of the region result in small variations of the value of the functional, then we can express the functional f as the integral of the form omega. And footnote 24, mathematically one needs to be precise as to what these small variations are and what the space of regions is. Effectively, we need to define what it means for K surfaces to be differentiable. This is more in the scope of physical mathematics than reverse physics. Note that the standard mathematical definitions are inverted with respect to what makes physical sense. Mathematically, we first define the form and then its integration, and we may worry whether the integral exists or diverges. Physically, we first define the functional of finite regions and worry about the existence of an infinitesimal limit, the form under additional physical assumptions. This is important because, as we said before, it tells us that it is the functional that survives when the assumption fails, not the form. It also means that if we want to get a robust physical intuition, we should concentrate on the functionals, the finite objects, rather than the forms, the infinitesimal objects.
We therefore reach the following. Insight 1.77. Differential K-forms represent the infinitesimal contributions of an infinitesimally additive quantity Fk that depends on a K-dimensional surface. The issue, however, is that while we have a sense that mutatis mutandi, what does that mean?
Basically, making all the details work. That's what it means.
Yeah, that's a new one for me. An infinitesimally additive functional corresponds to a differential form. We would need to show that differential forms cannot represent anything else. We currently do not have such an argument, though. We suspect it should exist. One may first note that no measurement can really be conducted at a point, and therefore it has to extend, at least in principle, over a k-dimensional region. Therefore, we could argue that all measurements are functionals, additive or not. This means that we would need a map between the value of the components of the form at all points and the value of the functional over all regions. To reach our goal, we would need to show that this map can be established only if the functional is infinitesimally additive, which may not be a strong enough condition by itself. While we are already implicitly assuming the map to be differentiable, we could impose further requirements on the measurement functional. We could impose locality in the sense that changes of the form within a region must change the value of the functional for said region. It would also mean that changes outside the region do not affect measurements in this region. While we do not know whether these requirements are sufficient, these are the types of questions we would need to answer in order to have a fully physically meaningful treatment of differential forms.
So there you go, Tobias. These are all the things that I haven't finished figuring out, and if somebody wants to help me do that would be exactly appreciated.
Yeah.
Having generalized the idea of integration, let us now turn to differential operators such as gradient, curl, and divergence. Suppose that T is a scalar field like the temperature, then we have the following relationship. Gradient of T dot d gamma equals T at the endpoint minus T at the initial point. That is, the integral of the gradient of T along gamma gives us the difference of T evaluated at the endpoints, the boundary of the line. If F is a vector field like the force, we have surface integral of the curl of F dot d sigma equals the integral over gamma, which is the boundary of a surface sigma, F dot d gamma, which is just the work evaluated on the boundary gamma. That is, the integral of the curl of F over a surface sigma is equal to the line integral of F over the boundary. If B is a pseudo vector field like the magnetic field, we have volume integral of divergence of B dV equals the surface integral over sigma, which is boundary of V, B dot d sigma, which is the flux over boundary sigma. That is, the integral of the divergence of B over region V is equal to the surface integral of B over the boundary. Note the pattern. The integral of the differential operator applied to the bulk becomes the integral of the original object over the boundary.
Let us understand how this works in terms of functionals. Given the temperature, T of P, we can construct a line functional that, for each line, returns the difference in temperature at the endpoints. Given the work line functional, W at gamma, we can construct a surface functional that, for each surface, returns the work needed to go around the contour. Given the magnetic flux surface functional, phi of sigma, we can construct a volume functional that, for each volume, returns the magnetic flux over the boundary. In general, suppose we have a k functional, fk from sk to r. To each k surface, sigma k, we can associate a quantity, fk of sigma k. Now suppose we are given a k plus 1 surface, sigma k plus 1, while fk cannot act upon sigma k plus 1. The boundary, d sigma, that's a partial d, partial sigma k plus 1 is a k surface. Therefore, we can evaluate fk of d sigma k plus 1. Therefore, we can define the k plus 1 functional df of k such that df of k sigma k plus 1 was this arrow? Maps to fk of d sigma k plus 1. Which we call the exterior functional of f of k. Since the exterior functional is an additive functional, it will have a corresponding form that acts on the infinitesimal region. Conceptually, the gradient of t is the one form that corresponds to the boundary functional of t. The curl of f is the two form that corresponds to the boundary functional of the work W, the line integral of F. The divergence of B is the 3 form that corresponds to the boundary functional of the magnetic flux phi, the surface integral of B. The problem is, again, that the gradient, curl, and divergence are not expressed in a way that is easy to generalize.
Was it me?
Yes. It's in
Okay.
the chat, the order. So
Yeah, sorry. I thought I remembered. Given that all 3 operators are in terms of nabla, I guess, which in components is written partial I, we would like to write something along the lines of partial fk of sigma k plus 1 is an integral over k plus 1. Partial I0 wedge omega with k indices, and then integral over k dx's. We want to turn that into an integral over this surface where we basically cancel the first partial in the wedge. And then this is equal to f of the surface of sigma k plus 1. Is that roughly what it
yeah,
should be?
yeah.
Okay.
So if you should recognize it's basically the Stokes theorem, right?
Yeah,
So
it's
what we're basically doing is instead of defining the exterior derivative and then getting the Stokes theorem, we start with the integral ones and define the exterior derivative as the form that does the Stokes theorem.
in 3 dimensions, it's a Gauss theorem, and then there's a specific Stokes theorem in 2D, and then there's a general Stokes theorem, right?
There's a general Stokes theorem. Yeah.
Okay. Yeah, I remember.
So basically here we're saying, well, we know that there is the left side and the right side. We want to have some operator wedge that makes this thing work.
Okay. So the operation wedge, which we call the exterior product, must be such that we recover something consistent to the previous operations. That is, we need partial I wedge t is just partial I t. I guess t is in a functional now. Yeah, temperature.
The temperature, so it's a 0 functional. Yeah.
Yeah, 0 functional. Partial I wedge fj, which is a vector or covector, is partial ifj minus partial jfi, antisymmetric. And partial I wedge bjk, which is now pseudo vector or 2 form. Partial I jk plus partial jki plus partial kij. So that is no minus signs. Are those all the permutations or no? Those are
Right.
just
So
shifted
this
vectors.
would be in 3 dimension. This is the divergence because the jk would be on the perpendicular would be the I component. Right. So if you think of the magnetic field, you would have xy for one side, and then you would have z because that would be the z component of the magnetic field. So you would be taking the partial on the z component along the z component.
Yeah.
Right. So we need something that right now this looks different, and then I think later, I don't know if it shows that it's actually the same. Probably not, but yeah, this is what we want by the definition of the divergence. It is going to work.
Okay. These would be the expressions we need to recover the gradient, curl, and divergence, respectively. Let us study them to see the pattern. First of all, each expression takes a k form and returns a k plus 1 form by adding a derivation along each index. given that we have a derivation for each index, the number of terms matches the number of indexes of the final form, which is k plus 1. Each term changes index by taking a cyclic permutation. Recall that the forms are antisymmetric, therefore each permutation of two indexes introduces a minus sign. Okay, a cyclic permutation of k plus 1 elements corresponds to k pair swaps. If k plus 1 is odd, then each cyclic permutation will correspond to an even number of sign switches which cancel out. Okay. The pattern then generalizes in the following way. So
Yes, this
we have
is.
a sum,
So you
we
basically,
cyclic permute, and we get a sign, I guess.
yeah. So if you see what's going on, you start with everything ordered from 0 to k, and then you start switching to the left, right? The 0 becomes the 1 becomes the 2, and the 0 gets added to the end, right? And then you keep doing it until you get all the permutations, and you always have a minus sign in front that gets multiplied and multiplied because you're gonna switch the parity.
Mhm.
And then another way to just rewrite this is with the sum that goes from 0 to k, and you use the mod on the index to be able to do the permutation.
Beautiful.
Yes.
Okay. The use of mod k plus 1. Is there a symbol missing? Or
I
is that
don't. Yeah, I'll
fun?
make a note and I'll look at that. There's this that's double space that it's weird. Yeah.
Okay. Maybe just because a math operator or something.
Yeah.
Okay. But the use of mod k plus 1 um, in the generalized expression makes sure that the index jumps from ik to I0. So we don't get an index out of bounds error.
Yes, that is
This
the
gives
problem.
us a fully antisymmetric tensor which matches the gradient, curl, and divergence in the simple cases. This operation is called the exterior derivative. And there's a footnote. In principle, we could write the expression in different equivalent ways. Here we use cyclic permutations as it gives a more elegant expression.
Yeah, when you define the exterior derivative, you typically write it in a different way. But I find this it's a little bit more clear what's going on.
While we have the expression for the exterior derivative, we would like to understand why and how the expression works. Geometrically, we can imagine integrating or along a parallelepiped, which becomes so on the
Okay.
left.
Yeah, so this is the integral of the on the k plus 1 surface of the exterior derivative, and we're writing this in sort of components. And then what you do here, this horrible thing, is expanding the form along the parametrization. Now, what's important here is that when you're expanding in terms of the parametrization, you are gonna have something with the derivative where everything else remains the same. And now this part of the derivative is going to be essentially canceled by the corresponding integral. Right? So this integral on u0 with the derivative of u0, it gets canceled out, and then you just have the difference of what's at the boundary. And that's going to happen for every sides of the parallelepiped, right? So the first one took the u0, the second one will take the u1, the other one the u2, and so on, right? So effectively what happens is that you're calculating this integral over the boundaries. And that's what you get at the end, that you're integrating the form over the boundary.
what happens is that each direction of integration will match a derivative in the same direction, and therefore will reduce to the integrations of omega on opposing sides of the parallelepiped. This happens for each direction, and therefore the whole integral will reduce to the integration of omega on the surface of the parallelepiped. We have verified that equation 1.81, which is known as the generalized Stokes theorem, indeed works, and it includes as particular cases the gradient theorem 1.78, the curl theorem, and the divergence theorem. Okay.
Was it just for parallelepiped? In general, it works on any surface, right?
Right, because this is the parallelepiped in the parametrization.
Yeah.
So you might have something that is completely different, but as long as you have the parameterization will always go from from a specific value to a specific value.
Okay.
And even if the parameterization does not quite work like that, because the parameterization depends on the region, I mean, you can restretch the parameterization every pieces, or you can think of the whole integrals as the sum of little pieces of integrals, and then the boundaries that are in common cancel out and all that.
Yeah. Okay.
Another aspect of vector calculus is given by the following identities. The curl of the gradient of t is 0, and the divergence of the curl of f is 0. To generalize them, we note that the exterior product is an anti-commutative and associative operation. Therefore, we have 1.85. So just applying two exterior derivatives.
Yeah, so you have two exterior derivative, you do the wedge product between the derivatives themselves, and then you see that they are basically the same thing with the minus with the index. The index is inverted, so it's 0.
In other words, the exterior derivative applied twice returns 0, no matter on what form it is applied. Given that the curl is the exterior derivative applied to one forms, and the gradient is the exterior derivative applied to 0 forms, the fact that the curl of the gradient is 0 is simply an application of the more general property. The same applies for the divergence of the curl. As we saw, mathematically the property is easy enough to verify, but we get no insight into its meaning. To understand the geometrical significance of the generalized relationship, recall that the exterior derivative of the form is associated with the exterior functional. We should then look at what happens when we construct the exterior functional of an exterior functional. We have double partial.
Yeah, so the exterior function of the exterior function of f. So you do the first exterior functional, it just becomes the functional applied to the boundary. Then you take the other one, again, is going to be the functional applied to the boundary of the boundary. But for any set, the boundary of the boundary is an empty set, and the function of the empty set, since the function is linear, is additive, then it has to be 0.
In words, the exterior of the exterior functional of fk equals fk applied to the boundary of the boundary. However, the boundary of a boundary is always the empty set, and any functional applied to the empty set must be 0. In fact, since functionals are additive, we must have like the empty set is like a identity.
Basically, yeah. You can always do the union of the empty set with the surface, right? And so, and there are these joints.
Therefore, we can see that the identity partial wedge omega equals 0 for every form omega is ultimately a direct consequence that the double functional U.
No, this is a set. The boundary of a boundary.
Well, boundary of a boundary is empty set for every set U. This shows how studying differential relationships in terms of finite functionals can give a more geometrically meaningful picture.
The last element of vector calculus we need to generalize is the idea of potentials. That is, curl of f equals 0 implies f is the gradient of v, and divergence of b equals 0 implies b is the curl of a. These are generalized by the following formula, where partial I wedge omega with k indices equals 0 implies omega with k indices equals partial L1 wedge theta with k minus 1 indices. That is, if the exterior derivative of a k form is 0, then there exists a k minus 1 form whose exterior derivative is the original k form. Footnote
And then there is
28.
the big footnote that tells you the difference between closed and exact forms, because we are sort of making a little bit of sleight of hand here, but I don't know. We can skip it or we can look at it if you guys want. So Samir is gone, so next is Tobias.
Yeah. Okay. To sum up, we have generalized the idea of integration over k-dimensional submanifolds of an n-dimensional space, which leads to the idea of k-functionals over finite regions and k-forms over the infinitesimal ones. We have seen that the finite functionals...
Wait a second. Did I... Oh, no, sorry. Go ahead.
Yeah. We have seen how k-functionals induce k+1 functionals by acting on the boundaries of the k+1 dimensional regions. We have seen that the exterior derivative gives us the form associated to the exterior functionals, and that this operation generalizes the notion of gradient, curl, and divergence. While this does not exhaust all that can be done in differential topology and differential geometry, this is enough for what we need to use in the following sections.
Those already familiar with differential topology will have noticed that our notation and definitions do not quite match the ones typically used in math textbooks. The issue is that said notation and definitions do not match what we need to physically capture, and therefore it would be a mistake to employ them. Let us briefly see why. First of all, in the context of differential topology, vectors are defined as directional derivatives. That is, a vector v equals v with the upper index I times partial I is an operator that acts on scalar functions. A velocity, which in physics we think of as a vector, is not a directional derivative. In differential topology, a covector, I'm not going to read that, is defined as a map from a vector to a scalar number. Conjugate momentum whose components change as a covector is not a map. In differential topology, a differential is a covector, and it is the exterior derivative of the coordinate. This means that differentials are maps such that the differential of is that the
It's a differential of xi applied to the basis vector partial xj is equal to the Kronecker delta. So it's 1 if I is equal to j and 0 otherwise.
Okay. In physics, this is not how we think of differentials and integration. In fact, consider the expression, the integral of f. To write it in terms of invariant objects, we would have, so we expand f using the basis vectors, and we expand the differential, where those are the co-basis and basis respectively, And therefore we have the Kronecker delta, okay. So we obtain, and we expand.
So you have f applied to dx, then you expand f and you apply dx. You use the linearity, you take the dxj outside, you use the fact that you have the Kronecker delta, and you get the expression at I dxi.
Therefore, in physics, the differential dx is more properly thought of as a vector, where the dxi are the contravariant components, while f as a map from a vector dx to the differential df, which is what is integrated. Therefore, the differential is the vector, while the force is the covector. This is in contrast to the use in differential topology. Moreover, in differential topology, there is a notion of a single tangent space where all the vectors live, which is not compatible with the idea of units. Consider the basis partial I. Given that coordinates are expressed in different units, we cannot simply sum derivatives along different directions. For example, in polar coordinates, partial r may have units of inverse meters, while partial theta of inverse radians. Worst of all, a directional derivative is taken with respect to a parameter, which will also have units and physical dimension. For example, if v represents a velocity, the components vi would also depend on the units of space and time. This would mean that units of vectors, the tangent space of a manifold, depend not only on the physical dimensions of the space, but also on the physical dimensions of all possible parameters along which we may want to define a directional derivative. This would mean that the tangent space is not definable only in terms of units of the manifold itself, and therefore is not defined just in terms of the manifold itself.
The takeaway message here is the following. The mathematical tools we inherit from mathematics are not necessarily designed to capture the physical relationships we need to capture. Mathematicians only care about formal definitions, regardless of what or if they represent physically. In physics, we do not have this luxury. If we want to have meaningful physical theories, which is ultimately the goal of reverse physics, we need to revisit the mathematical tools we use to formulate them.
And by the way, this is a shift that happened. So this idea of thinking as a vector as derivation, it's a shift that happened, from what I gather, in the 1950s and the 1960s. If you take differential geometry books that are from way before that, the vector was defined as the differential displacement or anything that changes as the components of a directional displacement or the infinitesimal displacement. So basically what this is doing is just going back to those definitions that mapped more to the physics. And again, there is isomorphism between these definitions. So if you have studied the math in one way, you can always translate it. It's just that the translation is always a pain. So that's why I just use this notation that maps more to that.
No, actually, this is a very interesting point, because this is one of those definitions where there's two versions. One, they call it a physicist definition with the tangent vectors of the curve on a manifold, and the other is the algebraic, the mathematician's definition.
Yeah.
With the germs of the differentials, derivations of functions. So, like this was a main thing. Like when I was doing the readings I was doing in my undergrad, my supervisor told me to learn both of them and use interchangeably, because sometimes it's convenient to think in one way as eating the functions, and sometimes you need the physicist definition.
The problem is even the tangent of a curve is not good for us.
Mhm.
So when you have when you define, and I made the note this. So the physics definition that you typically have is that you take a parameterized curve and then you define some notion of velocity, and then by basically making an equivalence class of curves. The issue is that the unit that you use for the parameter is physically significant. And so if you like that equivalence class makes sense only if you told me what was the unit. And the displacement instead, it's not, because the displacement is just the limit of sort of a sequence of vectors that converges decently. And there is no unit in that, it's just a sequential step. And so that's the part that even when you're doing with the equivalence class of curves, if you would reparameterize the curves, right, you would get a different tangent vector, but you would want to have instead the same infinitesimal displacement. So these are issues that I'd be great for me to have somebody like that really knows the math on one side to really go and get the details of what the problem is and try to sort of streamline it, because it causes a lot of confusion, because you never understand whether some things are defined with a parameter or not. So I have a notion of a vector field, right? Does that notion of a vector field depend on which unit I gave to the parameters of, let's say, of the curves that are the lines that were the field lines of that field or not? Because then when you're going to do Lie derivatives, okay, now does the Lie derivative depend on those parameterization or not? Like there are all these details that I was never able to, to sort of have to go through them and make sure. And because there are some things in physics that are going to depend on the parameterization. So when I talk about a velocity means that I have a trajectory. And if I have a trajectory, it means that I have two manifolds. I have the manifolds of time and I have a manifold on space, and then that's what I'm doing. But if I have in space-time, for example, in space-time, if I have just a differential, I have a differential in x and a differential in y. And now differential in x and differential in t. And now the velocity is the ratio between the two differentials. And meaning that if I have a tangent on a curve, on a word line in space-time, right? Whenever I reduce the delta t, I will reduce the delta x as well. And the ratio between the two at the limit is the velocity, which is a completely different object than the one that I had before. There was a map between them. And that tells you that the parameterization that you have on the word line is absolutely irrelevant, right? That parameterization, so whatever I define when I'm on space-time, the parameterization of the word line are significant. You can parameterize however you want, but the ratio between the two differential as things decrease, that's the physics. And so there are all these details that I know that they need to be taken care of carefully. I never had the time to go through it, but this is something that I'd really like to have somebody help me understand how the things work and exactly how it's different from what, So I hope that made sense, Rudra. Good. So question from the chat. Since this whole discussion is based on differential form, does it mean the Cartan formulation of differential geometry is more adapted to physical intuition than any traditional tensor-based one? I do not know what the Cartan formulation of differential geometry is. Let me,
They're the Cartan structure equations they might be talking about, where everything is like a tensor, is a vector valued or tensor valued form. So then you don't have to like take derivatives, you just take exterior derivatives. I think they use it in some versions of gravity.
Okay. Yeah, I guess I don't know enough.
I think mathematicians would agree, from what I know, that it's easier to work with the differential forms than, but then again, that's a biased view, because you can't tell the physicists to drop all their indices and just switch like that, because you take any university level course in general relativity, you'll have to work with indices.
Yeah, and the indices, I find it that are very useful to keep track of what's going on in the physics. So a lot of the time when I like even the reverse engineering of the action principle that we'll see later, I did because I started writing things in index notation so that I could understand so I find that the index notation is like nice to study, I don't know, invariance or general structure. But then if I really want to understand what's happening, I just yeah, I completely get lost. So comments from Julius, since in practice we measure finite quantities in final region, should we apply this logic to geometry, i.e. take Regge calculus where everything is finite and then take the limit to retrieve differential geometry? So I don't know what Regge calculus is, but that's what I'd like to do. I'd like to start everything with finite things and take the limits. This is something that so on the physical mathematical sides where I am starting to sort of to try to understand how to rederive the nuts and bolts of everything. What is very nice is that we start with the notion of ensembles, and again, ensembles are already finite objects in the sense that they are always distributions on finite elements, and they have an entropy that also always has to be finite. And these ensemble spaces, they were trying to understand still some of these details, but there should be an intuition that they always embed in some type of topological vector space, so that you have a topology on a vector space that it's compatible, and that the entropy should give you a topology that is also locally convex. And locally convex topological vector spaces are exactly what you need to define differential, like say, derivative on a generic vector space. So not just finite dimensional vector space like the tangent of a manifold, but even in function spaces. And so there is a sense that if we say, okay, we start with these finite objects, the ensembles that are always on finite regions and stuff like that, there might be a sense where we can actually then rigorously derive the sort of the substructure that you need to then define calculus. This is something that I still have opened, but this is where I'm trying to go. So then not only I basically say I start with finite region and then I take the limit, but also I start with finite objects and I give you the elements that you need to be able to define limits that actually make sense in terms of differentiability. So these are all pieces that I still have sort of around. I don't know exactly how they all fit. There is enough to tell me that they should all be fitting. I just don't know exactly how in the specific. So these are all open questions for me, and if anybody wants to help me figure this out, I would be ecstatic. Okay, any other questions? Okay, so everybody, thank you for following. For you, Julius, and thank you everybody else who is gonna watch this later. If you do watch this later, do put a comment so that I know who you guys are, because it's to know that there are actually people watching this makes it a little more sense for us to keep doing it. Okay, so thank you again, and see you next time at 11. Oh no, wait! I won't be here next time. Let me check my schedule. I will be away for travel in the next 2 weeks, though I might be able to join from a hotel next week. So, but I will know only when I am there. Or should we just skip for 2 weeks and that's it? What do you guys feel?
I mean, I'm flexible. If you tell me on the day, like it's gonna happen, I will show up. If not, then
Yeah,
not.
Yeah,
like my
same
issue,
same for me.
I don't know what's gonna happen for the streaming. So here I have a nice position to do live streaming and everything, and I don't know what's gonna happen when I'm there. So, okay, so I'll just let you know on Discord what's gonna happen. Okay, bye.
Have a nice weekend, everyone.
So thank you.
Thanks,
Bye.
you too. Bye.
Bye.
Bye.